Young and numbering in the billions, we fill a tiny space on our humble planet. 93 million miles away, the source of nearly all our energy and life burns. We may know much about our lives, but what about the sun's? What is a star's life like? What does it do, and what can a star become? In order to find out what occurs during the life of a star, we must start at the beginning. This is a nebula, a massive cloud of interstellar dust, plasma, helium, and mostly hydrogen gas. Most are larger than any star, as they produce countless children. All stars begin the same way. Gravity begins to pull the gas and dust in the nebula together, forming a dense ball. This is the protostar phase. Eventually, the protostar becomes dense enough to begin nuclear fusion. This process converts hydrogen, the star's fuel, into helium. Nuclear fusion produces light, heat, and eventually enough radiation pressure to stop the protostar's gravitational collapse. The activation of nuclear fusion has brought the star into its life. Its protostar phase is over and the main sequence phase has begun. The future of a star begins after the protostar phase. All stars enter a main sequence, but their lives will now hinge on one important thing: their mass. Stars can be put into three categories: small mass stars, medium mass stars like our Sun, and supermassive stars. Let's take a look. A small star's life cycle is much more plain than its larger cousins. These stars will burn through their helium slowly, in billions of years, but after exhausting their supply, they will shrink down to white dwarfs. A medium-sized star like the Sun can lead a much more eventful life. For the first 9 billion years, the Sun will burn its supply of hydrogen. Eventually, like all things, it begins to run out. When the supply of hydrogen begins to dwindle, the star begins to cool and expand. The center of the star shrinks while the atmosphere grows. In an attempt to stay running, the star will now begin using its helium as fuel. The burning of helium happens much quicker than the hydrogen fuel stage. The end of the red giant phase occurs when the atmosphere of the star spreads out so far it dissipates. After 11 billion years, the medium star has ended its main sequence phase. It is now a planetary nebula centered on a white dwarf just like the small mass star. Finally, we have the supergiants. These are stars with incredible amounts of mass. Supergiants have so much mass that they can burn through their hydrogen fuel in mere millions of years. The star will then shift, like the medium mass star, to helium and expand, forming a red supergiant. After quickly consuming its helium, the supergiant will make desperate attempts to stay alive. Using intense amounts of gravity, it will begin fusing carbon, then neon, then oxygen, then silicon, working its way up the periodic table to iron. Once the star reaches iron, it can go no further. Iron nuclei are more tightly bound than any other heavier metal. Fusion beyond iron does not produce energy, but consumes it. The star will begin piling up a core of iron. The star will desperately fuse iron until it has grown so large that it can no longer support its own mass. Suddenly, the core will collapse as its electrons are driven into its protons, creating neutrons, neutrinos, and gamma rays. The shockwave formed by this sudden collapse causes the rest of the star to explode in a supernova. Supernova will sometimes release as much energy as other stars produce in their entire lives, and outshine their galaxies. The remnant of the star becomes a nebula surrounding a neutron star or pulsar. In the case of the largest stars, they can leave behind a black hole. Neutron stars are stars that have collapsed to a point in which all particles are neutrons. Neutron stars that spin and emit radiation beams are known as pulsars. Black holes are objects with so much mass not even light can escape their gravitational field. They can be detected with the use of X-ray telescopes. It is believed that a supermassive black hole sits at the center of our galaxy. Neutron stars come from stars with about 8 to 15 solar masses, while black holes originate from supernovas in which the star was larger than 15 solar masses. But what about everything that is left? What happens to the white dwarfs and the black holes? The leftover nebulas repeat the process. As for the white dwarfs and black holes, scientists are unsure. So far, the universe has not existed longer than their lifespan, and we can only speculate. The material in a white dwarf no longer undergoes fusion. While a white dwarf is very hot when it is formed, it has no source of energy. It will gradually radiate its energy away and cool down, and become a cold black dwarf. There is limited knowledge of black holes to begin with. Following the trend that nothing lasts forever, even these incredibly strong entities should eventually decay.